story. So, to be entirely honest, my origin story is actually weaved into the presentation slightly, but I do believe I'm possibly the youngest when it comes to the amount of time I've spent using Julia. I started using Julia about a month and a half ago. Yeah. And I'm right off the tin. That's quite a treat. So my name is Pontus Stenetorp, and I'm a postdoc at the University of Tokyo. And I'm quite happy to have this talk because I get to talk about two things that I really like, which is Julia and my main research topic, which is natural language processing. I also do quite a bit of machine learning in case you're familiar with it, but we'll go through that. So, first of all, that doesn't work. My bad. Let's get into this. Okay. So first of all, let's bring everyone onto the same page, because talking about why Julia is good for natural language processing without knowing a little bit about natural language processing is quite hard. So from now on also I'll be using this little abbreviation NLP because natural language processing is quite a bit of a mouthful. So let's feel it out. So essentially, what is NLP? That's a very valid question. Well, NLP is essentially artificial intelligence. But what we want to do is that we want to process natural language as opposed to artificial language, like Julia, for example, using computers. And the ultimate goal, like the holy grail that we're going for, is language understanding, which means that a computer would actually be able to understand human language. Now, as it turns out, we have a little bit of a distance to go in order to reach this. So most people don't really talk about language understanding that much, but everyone dreams of it. So the second very valid question, of course, is why is NLP? Why should we care about this? Well, there are several ways of looking at this. One of them is the theoretical. Language is quintessentially like the most important human-to-human communication interface. It is the API that we use in order to communicate with each other. Well, that is kind of an API, isn't it? Maybe not programmable in the strict sense, but yeah. And I mean, for example, when making this presentation here, I could think of no better way than using language. Come on. Images might work, but I mean, anyone that has used UML knows that that's better. And also, incidentally, it is also our storage format. When we want to describe our feelings, our experiences, we use language to encode that knowledge. And some of the amazing things about this is that it kind of makes us immortal, in a sense. The episode of Gilgamesh was written like 4,000 years ago, and still the author is speaking to us today, as clear as it would have been 4,000 years ago, and that is, to me, completely mind-blowing. Yet, language on, how to say, an understanding level, or like some sort of semantic level, is largely a mystery. We don't really have any good formal representations or good ways of processing language. Even though it's so natural to us, for computers it's actually quite difficult, which we'll get to that soon. From a practical standpoint, well, since we store most of our experience, our opinions, and things like that in language, it gives us a window into our minds. Or even more importantly, it can give us a window into the minds of thousands of people. If we analyze, for example, I remember this rather interesting Twitter analysis, I think it was a couple of years ago, about how is America feeling, and they were essentially tracking the sentiments of tweets across the day. So in the morning, America was feeling a bit grumpy, and then during midday around lunch, people got a little bit happier again, and happiest of all towards the evening and going home from work. And a couple of years ago, I think this was back in 2011, a blogger noticed this little interesting, rather practical aspect. We thought that anytime a movie with Anne Hathaway had a premiere, the stock price for Berkshire Hathaway tended to rise slightly, which was kind of the conclusion he had. So a lot of these quants and a lot of this algorithmic trading actually already scourged the net and tried to find interesting information. And apparently, it couldn't really differentiate between two Hathaways, so apparently it was buying when there was a premiere. Quite interesting. Well, let's look very quickly also at NLP history, because it's actually a little bit older than a lot of us may think. It goes back to at least the 1930s, which is when people started doing word-to-word translation using punch cards. So you would encode whatever you want to translate into a bunch of punch cards, and then you would roll the levers and you would get a translation out of it. But the real start was in the 40s and 50s, right after World War II. So during World War II, there was a lot of success with computers, right? I mean, we could crack codes. absolutely amazing stuff. So some people actually even hypothesized to say that, well, I can't see any reason why Russian isn't just English encoded. And also there was a lot of optimism, like for example saying that a lot of the ambiguities in language, probably quite few. I mean, this is not such a big issue. We'll probably have this solved in a decade or two. Okay, famous last word. In the 1960s and 1980s, what tended to happen was that people would hire a bunch of linguists. So you would have computer scientists working together with linguists, and they would construct these huge complex systems for things like translation and information extraction and things like that. Ah, yes, should click forward. And now from the 90s, in the late 80s, early 90s, there was this huge revolution. Because it turns out that these kinds of large-scale rule-based systems are rather brittle. So there was the statistical revolution. So now we had access to more sophisticated machinery. So we could actually look at the data and try to make the machine learn automatically instead of us trying to build those brittle rules. Now, of course, these statistical models have their own drawbacks. For example, they're very unpredictable, and the kind of errors they make are very unhuman. For example, I think there was the Google speech engine that any sentence that ended with, I think it was with, well, I think it was a word that had an IN at the end, and then there was a with, it would change that into he now endorses the iPad. I don't know if that was actually a statistical bug, but that is pretty much how statistical bugs tend to look. They don't make any sense to us. So it's been, well over 50 years. Well, where's HAL? 9,000 from 2001 Space Odyssey. Where are our flying cars? Where are our conversational robots? Okay, so let's go back to the 60s again, and this is going to be applicable. So according to legend, I don't know, it's written at least in Harper magazine, the head translator of the Eisenhower administration back in the 60s was essentially introduced to one of these translation systems. And he thought, and it would translate, of course, into Russian, or Russian vice versa, because hey, it was the Cold War. So he thought, okay, what's a good sentence I can give to this system? Well, out of sight, out of mind. And the machine span on and told him, if it's something well, okay, so maybe not exactly what he expected. Now, so he thought, okay, that's a bit short. Lack of context and everything. Let's give it something else. So, how about the spirit is willing, but the flesh is weak? To which the machine replied, the liquor is holding out, all right, but the meat has right. And I think, even though this goes back to the 60s, I think all of us can probably say that we can have equal amounts of fun with Google Translate nowadays, but it's getting better. At least I think it's finally not mistranslated already, which is very much appreciated. Even though we've seen bugs, for example, where it translates capitals. So if you write, for example, I went to Stockholm in Swedish, and you translate that into English, then all of a sudden Stockholm will turn into London. It is the capital we're talking about. So, as I said, they make mistakes which are different from us, but it's an open question. So why is it difficult? Why is language difficult? Well, I think the simple explanation is that context. It is simply about context. There is a local context. If I say, for example, I stood at the back, it can be the riverbank or it can be shades. But resolving that is actually quite tricky. We might even only have this sentence, and that actually is ambiguous. We don't know. There's also the social context, especially me who's Japanese. You don't ever have fun, by the way, with a translation engine. You can try Japanese to English and vice versa. It's going to mess up the social context and everything completely in Japanese, and then it's going to come back like complete nonsense in English. And there's also the historical context. We change the meaning of words. I mean, for example, the word gay is an excellent example. It's artificially. It's essentially we decided in the 60s. We decided to change the meaning of it, or rather add a meaning to it, and that's absolutely amazing. But for a machine, this is tricky, very tricky. So it's not maybe so much about decryption from one language into another. I would rather say it's compression. It's just that the compression table is the human experience and our social context and our historical context at the time, which makes it very difficult. So we would say that it's effectively complete, which means we need to be able to simulate a human being in order to solve these kinds of problems. It's a bit of a task. So the MLP, despite these how can I say, early issues, still lives on. I mean, big companies like Google, Facebook, IBM, they have groups working in particular on language. And those are like fundamental. These are just like some of my own favorite tasks. So for example, we do things like parsing, which means we analyze syntax rather than semantics of a sentence. We do things like word sensitive abbreviations, so we can know which kind of bank you're talking about. We do things like which are more practical in nature. We do things like sentiment classification regarding tweets. What do people think about Obama's speech? Was it good? Was it bad? What do people think about the latest iPad? And we also do things like voice recognition. I mean, I think most people have been playing around with things. Or companion. So I'm assuming that he's talking about Watson. So now we talked a little bit about the bad. Let's talk about the good, because there's a lot of good in it. Well, first of all, wow. Yeah, wow when it comes to numerical code. This runs fast and very nicely. Also, thank you very much for everyone that's doing the packaging. The packaging works excellently. As a person who has compiled, say, for example, Octave on an old CentOS installation, you know what I'm talking about. That takes about 12 hours. Not the compilation time, no, it's you reading docs. Julia tends to work with a make. And just simple make command and it works, and that's just beautiful. Also, extending data structures is really easy, and this is something that I don't know how often this is stated, but this is something that I as well find to be absolutely gorgeous in you, and that is that we can take the data structures and we can just add functionality to them and it works seamlessly. That's just awesome. Also, the syntax is almost too familiar, especially if you're coming from the Python world like me, and sometimes you mess up when you think you're typing Python, but hey, could be worse. Could have been a lot worse than that. So in general, people that I show it to seem interested and are quite happy. And yeah, it might be about time that people move away from the scripting languages, especially if they need this kind of performance. All right. So for the last part of my talk, I will talk about Alien, which was the thing I decided to do. So I've already now decided that okay, Julia is interesting to me, but I've only written like 50 lines of it, so maybe I shouldn't be betting my entire life on this. So I decided to, when not doing my primary research, to implement what is called a dependency parser. And a dependency parser is a rather complex machinery, and it takes a while to implement. So essentially, it takes a sentence like this one. I'm a huge fan of Japanese food. So it takes a sentence like I ate sashimi, and it decides that ate is the root verb, and you have an object, and you have an object and a subject. And it can take any sentence essentially and produce this kind of output. It's a rather complex machinery. And if you get a good one of these, you can publish. This is just a proof of concept one. I have a personal one as well. So there are several approaches to this. You saw, for example, that it's a tree. So one of the first approaches you might think about is like, okay, we'll try to enumerate a lot of the possible trees or do some pruning or something. But it turns out that even the most efficient versions of this is like AutoNQ. And that's pretty slow. If you want to process like the whole of the internet, this is far too slow. So there's an alternative which is transition-based variants, so they run in AutoN. This is quite amazing. And I'll show you soon. I'll show you right now how they work. So they work like this. You essentially have, is anyone familiar with like a shift-reduce parser? It is essentially a shift-reduce parser, and it turns out that using a shift-reduce parser, you can parse like 98% of all English using a shift-reduce parser, which is actually used for formal languages. This is absolutely amazing. This is the discovery that's like 10 years old. So essentially, you have a stack and a buffer. You put like this dummy root token on top of the stack, and then you put the words on top of the buffer. And then at each and every single step, you're allowed to either shift a token from the buffer to the stack, or you can pop one token off the stack, and you say that there's a relationship between this and the top of the buffer, or you can do vice versa. And those are the only operations you have. So this is the kind of thing I implement. So let's have a look at a couple of things where I think Julia absolutely shines when it comes to implementing this. So first of all, this featureization. I'm not going to show you, I don't want to slander my colleague. I love this colleague who's this code is from. But the code is going to look pretty ugly, so prepare yourself. This is featureization code. It looks at the structure of the buffer and the stack, and it essentially like mashes words together in order to generate features. So there's like, this is just a small subsum, by the way. There's like 50 to 200 lines of this. So saying like S0, S1, and then like punching in the words and the part of speech and everything into these things. And by the way, can anyone spot that there's a bug here? Because there is. And I for the life of me, I mean, I copied this. I mean, I came home in January and my wife was asking me like, why do you look so horrible today? And I said, okay, I've been sitting down all day and copying feature templates. And there's actually a bug in here. And I didn't spot it. It took a while for me to spot it. It's actually that there's actually a duplication of, I think it's like T0 and T0 and TWO, T0, TWO is a duplicate. Really, really difficult to spot. So we should realize something here. This is highly repetitive code, right? What do we do with highly repetitive code in Julia? Well, there's this awesome thing called macros. So I just implemented a macro for this instead. It generates highly efficient code. And this is the same features and the same feature templates. I have a little bit, there's a little bit more going on. I mean, there's a macro. But it was a lot easier to do this. And even more awesomely, since we can actually look at these things as expressions, when I was writing it, I came up with the idea, wait a second, I can just do a comparison between expressions inside of the macro. And then just do an assert and say that if I have previously seen this expression, tell him, stupid you have a duplicate. And that's exactly what I did. And I think I found about 5 or 6 bugs in the feature templates, thanks to that. Absolutely awesome. I'm really in love with macros, even though most people, when I tell them that Julia has macros, they go like, oh, like C? No. Not like C, my friend, not like C. Then once we have these features, we need to do a mapping. So we need to map these feature structures into indices. And in order to do this, at train time, you need to essentially, every time you see a new feature, you need to allocate a new index. So what I did for this is that I first created this little type here, so essentially just wraps a dict. This is a little bit like a default dict, but it has this incrementing number. So what it does is that you can get an ID for something. That can be anything, that can be mapped to an integer. And if it is not already allocated, you just allocate the next number. So first thing you throw in gets ID 1, second one gets ID 2. But one of the issues is that this is what you'll be doing when you're training your algorithm. If you're seeing something unknown at a later point in time, you don't want to be allocating more of these because then you would be allocating unnecessary memory. So, and this is where we can do things like multiple dispatch. So we can just create another one. So we can create another thing that has a default value, and you simply instead of returning +1, you're returning the default value. And the awesome things about Julia, right? Extending a data type like this in C or in MATLAB or anything else, well, not in C, but in Python or MATLAB or anything like that, would actually be quite tricky. This runs very efficiently, and it was really, really easy to make. I mean, this is what, like 30 lines or something? It's absolutely beautiful. Lastly, let's talk about learning. So now we have the indices, so we have like unique numerical identifiers, and we also have this way of creating features. So let's talk a little bit about the perceptron. So it's a simple thing. So you simply take like these states, which is like how the buffer looks and how the stack looks right now, and you have some sort of function that maps this into a d-dimensional vector. Then you have a set of ways. You want to take the, yeah, exactly. Been there, done that. And then you have a set of weights. You can think, if you're not familiar with machine learning, you can think of these weights as, say for example, like the goodness of something, like how well does this fit in. And then you have a function which just featureizes the configuration and then does a dot product with the weight vector. So you might think that it's very natural to just use like ordinary linear algebra for this, but it turns out that you have about 4.8 million unique features, actually more than that. And this is for the English data set I'm using. And for each and every single decision, about, what is that, 1/10,000th of a percent of all of these features are active. So it's incredibly sparse. It's disgustingly sparse. So a lot of people, when they face this problem, well, okay, so we'll implement some sort of sparse format for it. So in Python, for example, you would have some sort of format and you would probably store all of the indices, and then you would do a loop over that. No. You're not going to do a loop over that in Python unless you want to wait till the next ice age. So what people do is that they, of course, implement this in Cypher C. Not as pretty. Now, I think if you really want to have like a takeaway message of like some of the reasons why I love Julia is this. This is what you do in Julia. You simply write a function that takes a sets of indices, a set of weights. You write a for loop, and you simply sum up the score as you go, and then you return. And you're done. I mean, of course, apart from not having the inbounds, but well, kind of everything. So now we've been talking a little bit about, so what about speed? I mean, how good can I get? Because I can replicate the performance of previous models, can I also replicate the speed? Well, if you look at the system and the number of sentences per second that it can do, the state of the art, which is by a very nice colleague of mine implemented in Cypher, is just like manual memory handling and everything like that. Runs about 1,000 sentences a second. That's about as fast as we can get right now. My implementation, Alien, runs at about 600. So I'm not quite there yet, but this is quite respectable, especially as almost like a hobby project on the side for me. And I have not stopped optimizing yet, trust me regarding that. It's been optimizing this for like 2 years. I've only been optimizing it for like a month. So it's also fairly small. It's about 1,200 lines of Julia. And if you're interested, it's available online if you want to have a look at it. It might not be a really amazing use to you, but if you want to talk about it, or if you want to scold me over the horrible Julia code, because there's some horrible Julia code in there, trust me. I started by copying some of my old Python code. But yeah, so that's pretty awesome. And I really want to thank the core developers for making this possible, and also the wonderful Julia community, especially the people over at Julia on Freenet. You've helped me out quite a lot in the beginning regarding this, and I'm just getting started. Thank you.
Questions? So in your experience starting out in Julia, are there any things that you thought were not intuitive and that took you some time to figure out in your head? Like,
you mean like the thing that trips me up the most?
Yeah.
Yeah, one indexing. I'm getting better at it, but it still trips me up now and then. Also, I think that one of the things we could do, so I think a lot of us are spoiled. I mean, I remember the good old days when I was doing like Haskell back at university, and there's this awesome homepage for like what Haskell is telling you and what it really means that you have to use, because hugs back in those days were just talking complete nonsense. Sometimes the feedback we get from the Julia part, for example, is a little bit opaque, but I've learned to handle it, and it is getting better. I mean, that's one of the things I always tell people, like, there are downsides to a young language, but one of the main upsides is that things tend to get better, and they get better fast. It doesn't go through a committee. Well, it goes a little bit through a committee, but it doesn't go through a committee. It doesn't go through a committee that takes 4 years to build a draft, which only half of the people actually implement. So.
we had a question there.
Over here? Was there another question?
I don't want to be handling this, please.
Okay. Just curious about your experience in Japan. Some years ago, I went to the Earth simulator, which was visited. It was the fastest supercomputer in the world at the time, and I asked how they programmed, and they said, "Oh, we all use Fortran." And I said, "How do you get everybody to program in Fortran?" And this fellow had this great sense of humor. He said that in Japan, we all respect our elders. So what I want to know is, what is your experience in showing this brand new language in such a context?
So I demoed Julia to the students at the lab, I think about a week and a half ago. There was some interest, but most of them haven't really started using it yet. I also demoed, so I have another presentation, which is how I met Julia, that I showed to a lot of people now. So I was at our main conference, ACL, just recently, and there's a lot of positive feedback in general when looking at it. About respecting your elders, I know of, there's a lab, I'm not going to mention which lab, at Todai, so Tokyo University, where they're using this actually Koenig and Ricci C library, which is made by by the professor himself, and none of the students dared to ask him to throw it out, even though it's actually real Koenig and Ricci C style, which I don't think anyone here has actually seen.
Yeah, I'm just wondering if you know of any other people using Julia for other aspects of NLP, and in particular I'm interested in optical character recognition, because I have millions of pages of text that I'd like to turn into.
Yeah, I don't know of anyone working with like OCR in particular. I know of a guy that is Sasami-san, for example, that is currently running the Julia user group in Tokyo. He's interested in NLP, definitely. Otherwise, I don't really. I've seen a little bit of NLP-esque discussions on the mailing list, but it seems to be fairly sparse. I mean, I think one of the big reasons is that I characterize NLP a little bit, maybe unfairly, as having two kinds of people: machine learners and feature engineers. And the feature engineers are usually like the biggest group of people. And I think a lot of them are still quite fine with their scripting languages because of the heavy lifting. But people like me, who don't really feel comfortable in C++, rather critical next to C++. And I think we're going to see a little bit of a move, because it's not just me that's being displeased with having to work with Cypher and things like that. But yeah, I'll be happy to talk to you afterwards about OCR in particular.
what does alien mean? Which language is it?
Oh, alien. It's just Swedish. It's just like the first computational linguist in Sweden. It's the only computational linguist that actually will be deciding on a Nobel Prize. Unfortunately, it's the Nobel Prize in Literature because, hey, we don't have a Nobel Prize in computer science anyways.
So, perhaps one last question?
Sure. I mean, so since you've been talking a lot about neural nets, so it's obviously not your main thing. I would guess I'll ask a sort of radical question for this conference, which is why not use Lua?
Why not use Lua? I don't know. To me, Lua is very different in nature. I mean, Lua is like you have to do all the plumbing on your own. I mean, you can do something like Torch, for example. But one of the big issues with the neural community. Okay, so I do feature learning, like representation learning kind of stuff, and deep learning things. And one of the big issues is usually that language has this recursive structure. So most of the libraries that you can get, like say for Fiona and everything like that, tend to assume that you're working with images, which is just like this pipeline. So you take the pixels and you push them up one level, you push them up one level, you push them up one level. And this assumption kind of goes through if you look at Torch and if you look at Fiona. So it becomes easier to just say that we need something special for language.
Pontus again.